You know, when I look up at the moon, I see consistency. It's the definition of calm. It drives the tides. It keeps our axis stable. It's just this silent silver companion that's always been there. It feels permanent.
It's the ultimate reliable narrator of the night sky. It's comforting, really.
It is comforting. But then I started reading through the stack of research we have for today, and we are talking about heavy hitters here, monthly notices of the Royal Astronomical Society, Nature Geosciences, the Journal of Geophysical Research, and I realized that my view of the moon is, well, it's a mask.
That is a very evocative way to put it. Because if you strip away that calm, silver exterior, the origin story of the moon isn't a romance. It's a horror story.
It's a crime scene.
It is absolutely a crime scene.
Yeah.
And not just a simple hit and run. We're talking about a forensic investigation that involves planetary annihilation, vaporized rock, and a mystery that scientists are still literally right now trying to solve because the evidence doesn't quite add up.
That is our mission today. We are going to reconstruct the murder of the proto-Earth. We're going to look at how we got from a chaotic shooting gallery of a solar system to the clockwork Earth-Moon system we have today. And I have to warn you, the theories we are diving into, they get weird. We aren't just talking about rocks smashing together.
No, we're going to talk about donuts made of vaporized rock.
I saw that in the notes, synestias. That immediately caught my eye.
Synestias, magma oceans, isotopic fingerprints, and the possibility that the Earth essentially turned itself inside out to make itself habitable.
It's wild stuff. But okay, before we get to the vapor donuts, we have to understand the reigning champion. The theory that has been in the textbooks for, 40 years?
At least. The giant impact hypothesis. Or, as it's affectionately known in the field, the Big Whack.
The Big Whack, I love it. So set the scene for us. Rewind the clock 4.5 billion years. We are in the Hadean Eon. What does the neighborhood look like?
It's messy. I mean, you have to completely erase the image of the orderly clockwork solar system we see today. It's a construction site that hasn't been cleaned up yet. You have planets forming, but there's debris everywhere. Planetesimals, asteroids, comets. It's violent.
So it's a shooting gallery.
A cosmic shooting gallery, exactly. And the Earth, or what we call the proto-Earth, or Gaia, is there. It's almost fully grown, maybe 90% of its current mass.
Yeah.
Hot, it's rotating, has a silted surface, but it's alone.
But not for long, because lurking nearby is another protoplanet.
Right, and we call it Theia, named after the Greek Titan who was the mother of Selene, the moon goddess. Now, Theia isn't a small asteroid. This is a legitimate planetary body, roughly the size of Mars, a world in its own right.
And the part that really surprised me in the reading was where Theia came from. It wasn't just some rogue wanderer flying in from deep space at random, was it?
No, and that's a key point. Statistically, a random object of that size hitting Earth is incredibly rare. The theory suggests Theia formed at a gravitational sweet spot called a Lagrangian point, specifically L4 or L5.
Okay, for the listener who isn't an orbital mechanic, let's unpack Lagrangian point. I always picture it as a parking spot in space.
That's a great analogy. Think of the Earth and the Sun. Their gravity's pulling on everything. But there are these specific points in orbit, 60 degrees ahead of Earth or 60 degrees behind it, where all those gravitational forces, plus the centrifugal force of the orbit, they all balance out perfectly. It creates a sort of gravitational dimple, a safe harbor.
So if you park a planet there, it stays there. It's trapped in the well.
Exactly. It's a stable point. So you can accumulate dust, rocks, and eventually build a whole planet in that blind spot. The theory goes that Theia could have grown up right alongside Earth, hidden in this stable pocket for millions of years, just sitting there waiting.
That is unsettling. It's like having a roommate you don't know about living in your attic for 10 million years.
Until the attic gets too crowded or someone shakes the house. Eventually, Theia grew too big for that stable point to hold it, or maybe Jupiter shifted its weight and sent a gravitational ripple through the system. Venus could have played a role. Whatever it was, the stability broke.
And it started to drift.
It started to wobble. It begins to oscillate, swing back and forth on its orbital path, getting closer and closer to Earth's orbit with each pass until they finally meet.
And this isn't a fender bender. This is a planetary collision. Can we even comprehend the energy involved?
Not really. We're talking about an impact velocity of maybe 9 kilometers per second, and it hits at an angle the simulations favor about 45 degrees. It's a side swipe, but a deep one. It's not a head-on collision.
That angle is important.
Right. It's critical. A direct hit would have just merged everything or possibly destroyed both planets. But a glancing blow at that speed and angle does something very specific. It imparts a massive amount of spin.
So what happens to Theia in that moment?
Obliteration. Absolute obliteration. Theia is sheared apart. Its heavy iron core punches through the Earth's mantle and sinks, merging with Earth's core. But the outer layers, Theia's rock, and a huge chunk of Earth's own mantle are vaporized and molten. They are thrown into orbit.
So you have this ring of fire, molten rock, and gas circling the Earth.
A debris disk, a massive, superheated debris disk. And from there, gravity does the rest. Over a shockingly short period, some simulations say less than a century, maybe even just a few years, that debris clumps together. It coalesces to form the moon.
It's a neat story. I can see why it stuck around for 40 years. It wraps everything up in a nice bow. It explains the physics really well.
It checks 3 big boxes. We call them the constraints. Constraint 1, angular momentum. The Earth-Moon system spins with a lot of energy. A big off-center kick from a Mars-sized object explains that spin perfectly.
Right. It spun us up at the top and gave us our 24-hour day, or well, our 5-hour day back then.
A very fast day, yes. It also explains the moon's orbit. Constraint 2. The moon's tiny core. The Earth has a massive iron core that makes up about a third of its mass. The moon has almost none. Its density is much lower, 3.3 grams per cubic centimeter versus Earth's 5.5.
Which makes sense if the moon was made from the splash material, right? The rocky mantle, not the iron core.
Exactly. The heavy iron from Theia sank into Earth, leaving the lighter, rocky mantle material to form the moon. It's a perfect explanation for the density difference. And constraint 3, the moon is bone dry. We call it volatile depletion.
Volatiles being things like water.
Water, nitrogen, carbon dioxide, all the stuff that vaporizes easily. If you form a moon in a superheated explosion of that magnitude, all the water and volatile gases just boil off into space. They're gone.
So physics says yes. Angular momentum, check. Density, check. Dryness, check. Case closed.
It should be case closed. It was for a long time. But then we started looking at the chemistry. We got better at it. And that's where the isotopic crisis begins.
This sounds like a sci-fi thriller title, The Isotopic Crisis.
It's a nightmare for geochemists. Here's the premise. In our solar system, every planet has a unique fingerprint. We call it an isotopic signature.
Is this like a chemical zip code?
Think of it more like DNA or a regional accent. It all depends on where you grew up in the solar nebula, that big cloud of gas and dust that form the sun and planets.
How does that work? Why does location matter?
Because the nebula wasn't uniform. The temperature and composition varied with distance from the sun. So, for example, take oxygen. Oxygen has 3 stable isotopes, oxygen 16, 17, and 18. The ratio of those isotopes in a rock depends on the conditions where that rock formed. If you formed close to the sun, you have a certain ratio. If you formed further out, like Mars, that ratio is different. Meteorites from different parts of the belt, different ratios.
So if I give you a rock, you can measure these oxygen isotopes and tell me this is from Mars, or this is from an asteroid.
With incredibly high precision. We can spot the difference easily. It's one of the most powerful tools we have in planetary science. We could do the same thing with tungsten, titanium, chromium, lots of elements.
Okay, I see where this is going. If Theia came from a different place, even a little bit different, like an L4 or L5 point, it should have a different accent, a different zip code.
Exactly. It should have a distinct isotopic signature from Earth. And according to the giant impact theory, the moon is made mostly of Theia debris. Depending on the simulation you run, the moon should be 60% to 80% Theia material.
So the moon should look like Theia. This should have Theia's DNA.
It must look like Theia. It's the central prediction of the model. But when we took the rocks brought back by the Apollo missions, rocks that we know are pristine lunar samples, and we put them under our modern mass spectrometers,
What did we find?
nothing, no difference. The Earth and the moon are chemically indistinguishable. Their oxygen isotopes are identical to within a few parts per million. Their tungsten isotopes to titanium. It's like they were cut from the exact same cloth.
So the moon doesn't look like Theia, it looks like Earth.
It looks exactly like Earth, to a terrifying degree of precision. The DNA test says the moon is Earth's identical twin, not Theia's child.
Why is that a crisis? Couldn't Theia just happen to have the same fingerprint as Earth, like a long-lost twin?
That was the first proposed solution. Maybe Theia formed right next door, so it was made of the exact same soup. But we've run the numbers. We've looked at the isotopic signatures of everything we can get our hands on. The solar system is not homogeneous. The likelihood of a Mars-sized impactor having the exact same isotopic composition as Earth is less than 1%.
And science doesn't like relying on miracles.
We hate it. We call it special pleading. You can't just invent a 1 in 100 coincidence to save your theory. So we are stuck. The physics says the moon is made of Theia. The chemistry says the moon is made of Earth. They can't both be true.
Unless they mixed. I mean, if you smash two planets together hard enough, doesn't everything just blend into a smoothie?
That's the equilibration argument. The idea that the vapor cloud hung around long enough for the Earth stuff and the Theia stuff to mix thoroughly before the moon formed. But standard physics says no.
Why? Why can't they mix?
Time. The debris just cools too fast. Gravity pulls it together too quickly. It's like dumping a cup of coffee into a bucket of milk and expecting it to be a perfect, uniform latte in 1 second without stirring. It just doesn't happen. The moon creates itself before the mixing can finish. You'd get a swirly, uneven moon, chemically speaking.
Yeah.
And that's not what we have.
So the giant impact, the big whack, is in trouble. It explains the spin and the size, but it fails the DNA test.
It fails hard. And this failure drove scientists to the edge. They had to find a way to mix the Earth and Theia completely. They needed a bigger event. They needed more energy. They needed more spin.
And that leads us to the donut.
The synestia?
I still can't believe this is a real scientific term. Synestia? It sounds like a medical condition. I'm sorry, you have a bad case of synestia.
It comes from the Greek syn, meaning together, and Hestia, the goddess of structures and architecture. Sarah Stewart and Simon Locke proposed this, and it blows the standard model out of the water. It's a radical idea.
What is it exactly? Because I'm picturing a glazed donut floating in space.
Imagine the standard impact again, that Mars-sized object hitting Earth. But this time imagine the Earth is already spinning incredibly fast.
How fast are we talking?
Really fast. A day is maybe 2 or 2.5 hours long.
Whoa, that's dizzying.
The Earth is spinning so fast it's almost flying apart. It's right on the edge of stability. Then you hit it with a high-energy impact. The energy release is so massive that the rock doesn't just melt, it vaporizes. But because of that high spin, that high angular momentum, the vapor can't just form a ball.
Why not? What's stopping it?
It hits something called the co-rotation limit. Basically, the equator of the planet is moving so fast that the material there is already orbiting as fast as a satellite would. The thermal expansion from the impact pushes the vapor cloud outward, and the planet.
Yeah.
It puffs up. It inflates.
It puffs.
It expands into this massive, continuous fluid structure. And crucially, it's not a planet with a ring around it. The planet becomes the ring. It looks like a giant, glowing, red-hot bagel made of rock vapor.
So the Earth isn't a sphere anymore, it's a cloud.
It's a continuous medium. There is no surface. You could fly a spaceship from what we call the surface deep into the center and never hit solid ground. It's all just increasingly dense vapor and supercritical fluid, thousands of degrees hot.
And where's the moon in this nightmare donut?
That's the beauty of it. The moon forms inside the donut.
Inside the vapor, how does that work?
Because the whole thing is a turbulent, boiling cloud. The mixing is incredibly efficient. The Theia material and the Earth material are churned together for maybe 100 years until they are one completely homogeneous soup.
That solves the isotopic crisis.
Yeah.
If they are all stewing the same pot, they have to end up with the same flavor.
Exactly. It solves the biggest problem with the standard model. Then, as this synestia starts to cool by radiating heat into space, droplets of magma rock rain start to condense out of the vapor.
Rock.
Literally, most of this rain falls down into the center to rebuild the Earth. But some of it rains onto a small seed, a gravitational clump, orbiting in the cooler outer regions of the donut. That seed grows and grows.
It grows into the moon, so the moon is basically a droplet of Earth vapor that condensed and got away.
A detachment of the Earth is a good way to think of it.
Yeah.
It explains why the chemistry is identical. It explains the dryness because it formed at 4,000 degrees Kelvin. It explains the low iron content. But the cost is that we have to accept that for a few hundred years, the Earth wasn't a planet. It was a burning, spinning donut of vapor.
That is a terrifying image, but it's elegant. However, it's not the only new theory on the block, is it? Because the synestia assumes one massive, lucky hit, a very specific kind of hit. But what if we didn't get hit once? What if we got mugged?
The multiple impact hypothesis.
The death by 1,000 cuts theory.
Exactly. This theory gains traction because giant synestia-forming impacts are rare. They require very specific conditions, but smaller impacts. In the early solar system, those were happening every Tuesday. They were common.
So walk me through this one. How do you build a big moon out of small hits?
It's a construction project over millions of years. You get hit by a smaller protoplanet, maybe a tenth the size of Theia. It's still a huge impact, but not a world-vaporizing one. It kicks up some debris. That debris forms a small moonlet, maybe a fifth the size of our moon.
Okay, so we have a mini moon.
Then, a few million years later, wham! Another impact. It creates another debris disk. That disk forms another moonlet.
Now we have traffic in orbit.
We do. And eventually, those moonlets interact gravitationally. They migrate outward, away from the Earth. They catch up to each other, they collide, and they merge.
Like snowballs rolling together to make a bigger snowman.
That's the idea. The simulations using advanced codes like Swift show that if you have a chain of maybe 10 to 20 such impacts, you can build an Earth-Moon system with the right mass and angular momentum. And the beauty here is that you get to average out the chemistry.
Right, because if you get hit by 20 different rocks from 20 different places in the solar system, the average flavor might look a lot like the average Earth flavor. It solves the isotopic problem in a different way.
It relaxes the constraints. You don't need one perfect isotopic twin. You just need a statistically average beating. Each impactor contributes a little bit of its own isotopic flavor, and it all averages out in the final product.
But there's a catch, isn't there? I remember reading about a problem with keeping the moonlets in orbit. It sounds delicate.
It's a huge dynamics problem. It's hard to keep a moonlet waiting around for the next one to show up. Often the next impact disrupts the orbit of the first one, or the moonlets collide too fast and shatter rather than sticking, or they just get ejected into space. It's a very delicate orbital ballet to get them all to merge into one big rock without losing them.
So pick your poison. A giant vaporizing donut that rewrites the definition of a planet, or a delicate game of orbital pool with 20 different rocks over millions of years.
That is the state of the science right now. We are trying to fit a puzzle together where half the pieces were vaporized 4.5 billion years ago. Both theories have strengths and weaknesses, and the community is actively debating them.
And we should mention, before we move on to how the Earth healed from all this, that there is a graveyard of discarded theories, ideas that sounded good at the time but just couldn't survive the math.
The also-rans of lunar history. It's important to remember them, to see how the science evolved.
I always had a soft spot for the capture theory, the idea that the moon was just a wandering planetoid and Earth's gravity snagged it like a catcher's mitt. It's romantic.
It is romantic, but physics hates it. It's a problem of energy. For Earth to capture a body as big as the moon, you need a way to slow it down. It's coming in fast. Without a thick nebula of gas to act as an air brake, and the nebula was mostly gone by then, a passing object would just swing by Earth, get its trajectory bent, and keep going back into deep space.
So it's a flyby, not a capture, a gravitational slingshot.
Exactly. And even if you somehow did capture it, the orbit would be wild, highly elliptical, maybe going the wrong way, not the nice, nearly circular equatorial orbit our moon has. It doesn't look like a captured prisoner.
And then there was the fission theory, right? Darwin's son, George Darwin, proposed this, that the early Earth spun so fast a chunk just flew off.
Right. He famously thought the Pacific Ocean basin was the scar where the moon ripped out. But for that to happen, Earth would have to be spinning once every 2 hours or less.
Which is similar to the synestia spin requirement.
It is, but the difference is the mechanism and the energy. In fission, the blob just flies off. But the total angular momentum of the Earth-Moon system today just isn't high enough to support that past.
Right.
We can calculate how the spin has slowed down over time due to tidal forces, and the numbers don't add up. We'd have to lose a huge amount of angular momentum somehow.
And co-accretion, that they just formed side by side like siblings from the same dust cloud.
That fails the iron test. That's the nail in the coffin for co-accretion. If they formed from the same cloud of dust at the same time, they should have the same bulk composition. Specifically, they should both have big iron cores. The moon doesn't.
Okay, so the moon is definitely a child of violence, whether it's one big crash or a series of them. But let's zoom out a bit. All of this, Theia, synestias, moonlets, is happening in the context of the Earth trying to build itself.
Right. We can't look at the moon in isolation. Earth was growing up too.
Yeah.
And the way it grew up is fascinating because our understanding of that has changed recently too.
Let's talk about that growth process, because the source material mentions something called pebble accretion, which sounds adorable, honestly.
It sounds cute, but it's a powerhouse mechanism for building planets fast. For a long time, we thought planets grew by big rocks smashing into big rocks, planetesimals hitting other planetesimals.
Demolition derby style.
Right. But that process is slow and inefficient. You get a lot of fragmentation. New models suggest that aerodynamic drag played a huge role.
Aerodynamic drag in space? I thought space was a vacuum.
In the early solar system, there was still a lot of gas left over in the protoplanetary disk. It wasn't empty yet. So as small, centimeter to meter-sized pebbles moved through this thin gas, the drag acted like a headwind, slowing them down.
Like sticking your hand out of a car window.
Exactly. This friction caused them to lose orbital energy, drift inward toward the sun, and get swept up by growing planetary embryos much more efficiently than big rocks would. It allowed the cores of planets like Earth and Jupiter to bulk up rapidly. Earth essentially vacuumed up these pebbles.
But wait, if we were vacuuming up everything, why are we this size? Why aren't we bigger? And more importantly, why is Mars so small? I mean, Mars is tiny compared to Earth.
That is the famous Mars problem, and the solution might be the Grand Tack hypothesis. This involves Jupiter, the bully of the solar system.
I knew it! Jupiter's always involved.
The theory is that Jupiter formed early, and due to its interactions with the gas disk, it migrated inward toward the sun. It got as close as maybe 1.5 astronomical units right where Mars is today. As it moved, it acted like a giant snowplow. It scattered or ate up a lot of the material in that region.
And then it just left.
It tacked, like a sailboat. It reversed course and migrated back out, likely because Saturn had formed and its gravitational pull started tugging Jupiter back out. But the damage was done. It had starved the region where Mars was trying to form of its building blocks. That's why Mars is so small. It's only about 10% the mass of Earth. It's a planetary embryo that never got enough food because Jupiter ate its lunch.
Poor Mars. But this explains why Earth and Venus are the biggest of the terrestrial planets. We formed in the sweet spot that Jupiter missed.
Exactly. But Earth paid a price for all this growth. All this accretion pebbles, planetesimals, Theia generated immense heat. And this leads us to one of the most significant events in Earth's history, the Iron Catastrophe.
That is a metal band name if I ever heard one, the Iron Catastrophe.
It's intense. And it was a literal catastrophe for the structure of the planet. When Earth first formed, it was a more or less homogeneous mix. Rock, metal, silicates, everything jumbled together like a big granola bar.
But today, we have layers. Crust, mantle, core. How did we unmix the granola bar?
Heat. As the Earth got bigger, the pressure inside increased and it got hotter. Radioactive decay of short-lived isotopes, specifically aluminum-26, heated it from the inside, and the constant barrage of impacts heated it from the outside. Eventually, the temperature rose above the melting point of iron.
And once the iron melts,
Iron is much denser than rock, so gravity takes over. The molten iron starts to sink. But it doesn't just trickle down. It likely pooled and then collapsed in massive diapers. Huge continent-sized blobs of molten metal plunging toward the center of the planet.
and as that heavy metal sinks, it releases energy, right?
Massive amounts of gravitational potential energy. This is the key. The friction of its sinking releases energy, which turns into heat, which melts more iron, which makes it sink faster. It's a runaway thermal process. This is the catastrophe. In the geological blink of an eye, maybe less than 30 million years, the Earth completely reorganized itself. It differentiated, the core separated from the mantle.
How do we know it happened that fast? 30 million years is nothing in geology.
We use a very clever clock called hafnium-tungsten chronometry, HF-W.
Walk us through that. How does that clock work?
It relies on chemical preferences. Hafnium is lithophile. It loves rock. It wants to stay in the mantle. Tungsten is siderophile. It loves iron. It wants to sink into the core.
Okay, so they separate. Hafnium stays up, tungsten goes down.
Right. But here's the trick. One isotope, hafnium-182, is radioactive. It decays into tungsten-182, but it decays very quickly. Its half-life is only 9 million years. It's all gone within about 60 million years of the solar system's formation.
So it's an extinct isotope.
Exactly. So here's the timeline. If the core formed late, after all the hafnium-182 had already decayed into tungsten-182, then all that tungsten would have sunk into the core along with the other tungsten. The mantle would be depleted.
Okay, that makes sense.
But if the core formed early, while hafnium-182 was still around and decaying, then the hafnium would be stuck in the mantle. As it decayed, it would produce new tungsten-182 that was also trapped in the mantle, because the iron had already gone down. The door to the core was closed.
So by measuring the amount of tungsten-182 in the mantle today, we can see if the door closed early or late.
And when we look at Earth's mantle, we see an excess of tungsten-182 compared to meteorites. That tells us the core formed while hafnium was still decaying. The clock tells us the iron catastrophe happened in the first 30 million years. This is crucial because when Theia hit, Earth already had a core. That's why Theia's core could merge with ours, and why the debris thrown into orbit was mostly mantle rock, not iron.
It's all connecting. The iron catastrophe set the stage for the low-density moon. But this heat, if the iron catastrophe melted the interior and Theia melted the exterior, Earth must have been a complete mess.
Mess is an understatement. For a time, Earth was a magma ocean.
Not a magma pond, a global ocean.
A global ocean of liquid rock, likely extending thousands of kilometers deep, maybe all the way to the core mantle boundary. And it wasn't just Earth. The sources point out that magma oceans are a universal feature of planet formation. Vesta, the large asteroid, had one. Mars had one. The Moon definitely had one after it formed.
I want to touch on the lunar magma ocean because we can actually see the results of that today, right, when we look at the moon.
We can. It's one of the clearest examples. When you look at the Moon, you see the dark patches, the Maria, and the bright white highlands. Those white highlands are the direct result of the lunar magma ocean cooling.
How so?
Think about a lava lake freezing, but on a planetary scale. As the molten moon cooled, certain minerals began to crystallize out of the liquid. Heavy minerals like olivine and pyroxene crystallized first and sank to the bottom. But a lighter mineral, a type of plagioclase-filled spar called a northicite, is less dense than the magma. It floated.
It floated like ice cubes in a drink.
Exactly. It formed a flotation crust, a white, frothy crust of a northicite rock on top of the magma ocean. That's what we see today as the lunar highlands. It's the ancient primordial crust of the moon, solidified from that magma ocean.
And underneath that crust, the leftover liquid got really weird, right? I saw the acronym CREEP in the notes. K-R-E-P.
Ah, yes, CREEP. It stands for potassium, K, rare earth elements, R-E-E, and phosphorus, P.
It sounds like a generic villain name. Dr. Creep.
It does, but it's actually the dregs of the magma ocean. As all those other crystals formed, they rejected these particular elements. They don't fit nicely into their crystal lattice structure. So these incompatible elements get more and more concentrated in the last little bit of liquid magma. It's this chemically distinct layer that got sandwiched between the crust and the mantle. And because it's full of radioactive elements, it's been a heat source for billions of years.
That's fascinating. But back to Earth, we had a magma ocean too. And this brings up a chemistry puzzle that I found in the notes that blew my mind, the rust problem.
The oxidation state of the mantle. This is a subtle mystery, but it's profound for the evolution of life.
Break it down. Why is Earth rusted?
So core formation, the iron catastrophe, requires what we call reducing conditions. Basically a chemical environment with a lack of free oxygen. That's what allows pure iron metal to separate out. But today, Earth's mantle is oxidized. It has a lot of its iron in an oxidized state, F2+ and F3+, flat like rust. The question is, how do you get an oxidized mantle if you just stripped out all the metal to form the core? The chemistry shouldn't work.
Right. Did we get a delivery of oxidized material later from asteroids or something?
That was the old theory, that a late veneer of oxidized asteroids hit us after the core formed and added the oxygen. But the math doesn't quite work to explain the amount we see. The new mechanism, supported by high-pressure lab experiments, is called disproportionation.
That's a $10 word.
It is. It basically means one thing splits into two different things. Deep in the magma ocean, the pressure is immense. We are talking hundreds of gigapascals. At those pressures, iron in the form of Fe2+, ferrous iron, becomes unstable. It spontaneously splits into two things, F3+, ferric iron, which is highly oxidized, and pure metallic iron.
It splits itself into rust and metal.
Essentially, yes. But pure metal's heavy. It sinks to the core. But the Fe3 plus the rust is happy to stay in the silicate mantle. So by forming a core at extreme pressure, Earth actually oxidized itself from the inside out. It's a self-regulating process.
That's wild. So the pressure of the planet itself forced the chemistry to change.
Exactly. And this explains why Mars is different. Mars is smaller, it has less pressure inside, so this disproportionation process didn't happen as efficiently. That's why Earth's mantle is more oxidized than Mars's mantle. It's a direct result of our size.
Size matters.
And planetary geochemistry, absolutely.
Speaking of things deep in the Earth, we have to talk about the blobs.
The LLSVPs, large, low shear velocity provinces.
These are huge structures deep in the mantle, sitting right on top of the core, right? We know they're there because seismic waves from earthquakes slow down dramatically when they pass through them, and for a long time we didn't know what they were. But there's a provocative theory in our source stack linking them to Theia.
This is one of the most exciting recent developments, and it's mind-bending. Some of the newer, higher-resolution impact simulations suggest that when Theia hit Earth, not all of it vaporized and mixed in. Theia's own mantle might have been a bit denser than Earth's mantle, maybe because it had more iron oxide, and parts of it could have remained as coherent chunks.
They sank.
They sank. They plunged through Earth's magma ocean all the way to the bottom of the mantle and settled there, like two continent-sized piles of alien sediment. So these LLSVPs, these massive blobs under Africa and the Pacific, might actually be the physical remains of Theia's mantle.
That gives me chills. We might be standing on a planet that has the corpse of another planet buried deep inside it.
It's a plausible theory, It suggests that Theia isn't just gone, it's part of Earth's foundation.
Mm.
We are a chimera planet.
A chimera. Two bodies fused into one. It really changes how you look at the ground beneath your feet, especially since those blobs are linked to things like hotspots and supervolcanoes today. Theia is still affecting us.
It is. It's shaping our geology 4.5 billion years later.
But let's look at what happened after the magma ocean cooled, because this is where Earth became habitable. And Mars didn't. What was the fork in the road?
The cooling of the magma ocean is the critical turning point. When a magma ocean freezes, it can do one of two things. It can form a stagnant lid, a solid, immobile single-plate crust that just sits there and gets old. Or it can break into plates and start moving.
Plate tectonics, the engine of the Earth.
Right. Mars almost certainly went the stagnant lid route. Its magma ocean froze, formed a thick crust, and that was it. Game over. No recycling. That's why it has the largest, oldest volcanoes in the solar system. They just sat over one hotspot and never moved.
But Earth got mobile plates. Why? What was different here?
Water seems to be the key ingredient. Water acts as a lubricant for the crust. It gets into the rock, alters its viscosity, lowers its melting point. It allows for subduction, where one plate can bend and slide under another, to happen. Because Earth kept its water, or got more of it delivered, the crust remained weak enough to broke and move. Mars lost its water, and its crust seized up.
And that movement is crucial for life, right? It recycles carbon, it keeps the climate stable over geological time.
Absolutely. It's the carbon silicate cycle. It acts as a planetary thermostat. Without tectonics, Earth might have ended up like Venus, a runaway greenhouse, or Mars, a frozen desert.
But there's another shield we need. Tectonics keeps the temperature right, but we need protection from the sun, the magnetic field.
The dynamo. To generate a magnetic field, you need a churning, convecting liquid metal core. Usually we think of the inner core freezing as the power source for this. As the inner core solidifies, it releases heat and lighter elements that stir the pot.
But wait, the inner core is young, right, relatively speaking.
Very young, maybe only 1 billion years old, or even less. But we have evidence from ancient rocks of a magnetic field going back much further, to 3.5 or even 4 billion years.
So what powered the shield before the inner core formed? If the engine wasn't built yet, how was the car running?
This is a huge puzzle, and one of the papers suggests a really cool solution. The magnesium precipitation hypothesis.
It's raining magnesium in the core.
Sort of, in reverse. Remember how violent the Theia impact and the early accretion were? The temperatures and pressures were so high that elements that usually stay in rock, like magnesium, might have actually dissolved into the liquid iron core.
Okay, so the core is polluted with magnesium.
Right. But as the core slowly cools down over billions of years, that magnesium becomes less soluble. It wants to get out. It precipitates out. It solidifies. But magnesium is light, so it floats upward through the liquid iron to stick back onto the bottom of the mantle.
So it's snowing up.
Snowing up. And this upward movement of a light element stirs the core. It creates powerful convection currents. This mechanism could have been powerful enough to run Earth's magnetic dynamo for billions of years before the solid inner core ever appeared.
And we really, really needed that shield, didn't we? Because the young sun wasn't the friendly yellow ball it is today.
No. The young sun was a T-Tauri star. It was a teenager. It was violent, angry. It had massive solar flares, a solar wind that was maybe 1,000 times more intense than today's. Without a magnetic field, that solar wind would have just sandblasted our atmosphere and our water away.
Which is what happened to Mars.
Exactly what we think happened to Mars. Its smaller core cooled faster, its dynamo died, and the solar wind stripped it bare.
But we had help. One of the papers mentions coupled magnetospheres. This sounds like a sci-fi shield technology.
It's a really cool concept. 4 billion years ago, the moon was much closer to Earth than it is today. Maybe 10 times closer.
Right, slowly drifting away a few centimeters a year.
Back then, it was so close that its own magnetic field, which it had at the time from its own small molten core and Earth's magnetic field, might have actually connected. They would have draped over both worlds and coupled together to form a massive combined shield.
A double shield.
Yes. This extra strong two-planet magnetosphere would have provided a much larger obstacle to that fierce solar wind. It would have protected Earth's fledgling atmosphere during that critical T-Tauri phase when the sun was at its nastiest. The moon may have literally saved our atmosphere.
So not only did the moon's formation define our spin and our tilt and our tides, but its presence might have saved our air. It's a true partnership.
It is. We often look for Earth-like planets out there, But maybe we should be looking for Earth-Moon systems. The interplay between the two bodies might be absolutely essential for long-term habitability.
This has been a wild ride. We started with a crime scene and ended with a protective embrace. Let's try to synthesize this for the listener because there are a lot of moving, chaotic parts.
Sure, let's try to build the timeline of catastrophes.
We tend to think of Earth as a rock that just formed. But the story the data tells is one of constant reinvention through violence. Step 1. Dust clumps into pebbles that get swept up by aerodynamic drag.
Step 2. Jupiter swings in like a wrecking ball, the grand tack, and clears out the neighborhood, starving Mars and defining the layout of the inner solar system.
Step 3. The iron catastrophe melts the entire interior of the planet. The core forms in a runaway process, and the clock starts ticking on the tungsten isotopes.
Step 4. Theia smashes into us. Maybe it's a big whack. Maybe it creates a synestia, that vapor donut.
Step 5. The moon forms from that debris, either from the splash of a single impact or the merger of many moonlets. Geochemically, it's a piece of Earth.
Step 6. The magma ocean that covers the planet slowly cools, creating our first crust and, through high-pressure chemistry, oxidizing our mantle from the inside out.
Step 7. Magnesium snow begins to fall upwards in the core, powering a magnetic shield that protects us from the angry young sun.
Step 8. The moon, orbiting much closer, links its own shield with ours to provide extra protection, saving our atmosphere from being blown away.
That is just an incredible sequence. It wasn't a construction project, it was a demolition derby that somehow resulted in a habitable planet.
Every single one of those violent events was a necessary step. Change any one of them, and we probably wouldn't be here.
And it leaves us with some lingering, almost philosophical questions. The synestia model in particular really sticks with me. If the moon formed inside the Earth's vapor cloud, does that mean the moon isn't really a separate body? Is it technically a detached continent that moved into the sky?
That's a provocative thought, but geochemically you could argue that's true. It is a piece of Earth that's separated and cooled in orbit. It's not a sibling or a cousin. It's an offspring or a detached limb.
And the other thought, those blobs, the LLSVPs, if those really are the remnants of Theia's mantle, then the alien planet that tried to destroy us is still here. We are standing on it. It's affecting our volcanoes, our magnetic field. Theia didn't die. It went underground.
It merged. We are Theia. Theia is us. The collision wasn't an end. It was a beginning, a fusion.
That is unsettling and beautiful at the same time. We have covered a lot of ground and vapor today, from the violent birth of the moon to the microscopic splitting of iron atoms that rusted our mantle. It really makes you look at the moon differently. It's not just a rock, it's a witness, and it's a survivor.
And it's the reason we are here. Without that collision, without that spin, without that magnetic coupling, we likely wouldn't be having this conversation. The moon isn't just a pretty light in the sky, it's a fundamental part of the Earth system.
So next time you see the moon, give it a nod. It's been through a lot. That's all for this deep dive. Thanks for exploring the chaos of the early solar system with us.
Always a pleasure.
See you next time.